Assalamualaikum and hi. My name is Ahmad Nabil bin Zulkifli. My metric number is B0319100066. I am from BITS S1G1. In this presentation, our group will be presenting about divide and conquer algorithm. We choose quicksort. So, what is quicksort? Quicksort is one of the most powerful and efficient sorting algorithm. It is a recursive algorithm with divide and conquer strategy. It will pick an element as a pivot and partitions the given array around the pivot. There are many different versions of quicksort that picks pivot in different ways. Quicksort has time complexity of big O and log n for average case and big O n square for worst case. Now we will see how quicksort works based on this picture diagram. So we will have the input like right here, and we will end up with an output that has been sorted like right here. So what will quicksort do is it will select an element as a pivot. This can be any element. In my case, I prefer the pivot to be the last element in the array. So I will choose 5 as the pivot. Now what will happen here is the number that is less than pivot will be placed at the left side of the pivot, while the number that is larger than pivot will be placed at the right side of the pivot. So 2, 4, and 3 is less than 5. It will be placed at the left side. And 8, 6, 7 is larger than 5. So it will be placed at the right side, like this. Now, as you can see, the pivot is already at its correct place. This process is called partitions. If we can ensure this for every element in the array, we can say that all the array is already sorted. Resulted by the partition, we will get two subarray, which is on the left side is the element that is smaller than pivot, and the right side is element that is larger or greater than the pivot. So now we will apply the partition to the left side of the subarray. The pivot that I will choose on the left side is 3, since it is the last element of the left subarray. So now all elements that smaller than 3 will be placed to its left, and the element that is greater than 3 will be placed to its right. As you can see, 2 is smaller than 3, so 2 will be placed at its left, and 4 is larger than 3, so 4 will be placed at its right. And now 3 is already at its right place. Okay, now if we try to apply partition to the subarray of the pivot 3, which is 2 and 4, nothing will really happen as the size is 1. This means that the element is already in its correct place. Now we will apply partition at the right side of our first pivot, which is 5, so the right side is here. 7 will be chosen as the pivot, and the element that has smaller value than 7 will be placed to its left, and element that has greater value than 7 will be placed to its right, like this. So as you can see, 6 is smaller than 7, so 6 will be placed to its left, and 8 is greater than 7, so 8 will be placed to its right. Okay, now as you can see, our array is already sorted, and this is our final answer. So that's all for introduction and picture diagram explanation.
Assalamualaikum and hello everyone. My name is DANISH bin Muhammad Noor. I am going to present to you about real-life implementation of quicksort. I am going to give you two examples, but I will explain only one of it, just to make you understand about quicksort. Before we go to the examples, I would like to remind you of what quicksort is. Quicksort is a divide and conquer algorithm. It picks an element as a pivot and partitions the given array into subproblems. Without further ado, let's get to the main point of my presentation. The two examples that can be solved by using quicksort algorithms are sorting a queue of students based on their height, and another one is sorting a set of poker cards based on their numerical values. I will explain how quicksort will operate to solve the given problem. Let's say these are a queue of students' height. As you can see, the queue is not sorted. Alright, so let's say the pivot is 165. We will need to find the position of pivot such that all the elements that is less than the pivot, currently the pivot is 165, should be on the left side of the pivot, and elements greater than the pivot should be on the right. So to achieve this, we will need I and J, where I will be incremented until it finds an element greater than the pivot, while J will be decremented until it finds the value less than the pivot. In this example, I will start at the beginning of the array, while J will start at the end of the array. As I mentioned earlier, increment I until it finds the value of elements greater than the pivot. We will compare the pivot and number I, the number 1, sorry. But remember that I will be incremented until it finds an element that is bigger than the pivot itself. So on index 1, you can see that 155 is less than 165. So I will move to the second index. Element inside index 2 will be greater than the pivot. Therefore, I will stop incrementing at index 2, while J will be decremented until it finds an element less than the pivot. In this example, J will stop at index 6. When both I and J have fulfilled their condition, they will perform a swap. After swapping, increment I again until the same condition is met. Also same with J, keep on decrementing until it finds an element that is less than the pivot again. So I will stop at index 3 and J will stop at index 4. Then it will perform another swap, and it will continue the incrementation of I and decrementation of J again. But this time, as you can see, J have surpassed I in decrementing. When index of J is less than index of I, then do not swap between I and J. the current position of J is supposed to be the location of pivot. So you just need to swap the location of J with the current pivot. So swap between 156 and 165. Therefore, when you swap the pivot 165 on index 3 or on J, as you can see, the pivot location is sorted. How do I know the element 165 is sorted? It is because on the right side of the array are elements that are larger than the pivot, while on the left side of the array are elements that are lower than the pivot. Remember that quicksort is recursive and it will divide a problem into subproblems. This is why it is called divide and conquer algorithm. After dividing into smaller problems, which is this will be divided into a new array, which is called a subproblem, and this will also be divided into a new array, also called another subproblem. It will choose another new pivot inside these subproblems, and it will swap between more or less with using the same procedure. So that's all from me. The quicksort will continue until it is sorted. It is fully sorted. So that's all from me. Thank you.
Hello guys, Assalamualaikum. I am HAZIM and I will be explaining the quicksort algorithm code using this pseudocode and its implementation. This particular function named as quicksort is where we pass the whole array in the first argument followed by the first array as start and the last array as end. Like any other array, it starts with a 0 and ends with the size -1, which in this case is 7. Let's look at the quicksort function body. What's going to happen is that they will be passed to a function named partition. After that, a recursion will happen whereby the arguments are passed to the quicksort function again but with different parameters. The first quicksort will partition the elements to the right and the second quicksort will partition the elements to the left. Now let's have a look at the partition function. Now this is where the magic happens. As usual, we choose the last element as the pivot. That's why we declare integer pivot is equal to array end, and p index is equal to start because we want to put it at the beginning, and then the program will execute the for loop. If array I is less than the pivot, then it will swap the current array value with array at the p index, and p index will move to the second element, hence the partition index plus plus. If the condition is false, then it will not execute the swap and p index increment. P index will stay at its current place. Once the for loop is done looping, it will execute the swap command that swaps the array value at p index and the array value at the end. After that, it will return p index. The p index will be used again in the recursion quicksort. The process repeats and the program will exit when the condition start is lesser than n and the quicksort function is false. If it is false, the program will not execute the if body. So let's test this. Okay, the code works. As you can see here, the swapping process is executed when it is true, and it repeats because of the recursion. If you see a message saying partitioning, it means it is moving to another section of partition that is smaller than the previous one. To exit, the condition start must be bigger than n. So there you have it. The elements are sorted in the n and ascending order. That's all from me. Assalamualaikum warahmatullahi wabarakatuh.
Hello and selamat sejahtera. My name is Muhammad Daniel bin SLUHUDIN HAMDAN. ID metric is B03-191-0495. We'll be presenting about quicksort versus merge sort. Previously, we've seen about what is quicksort and how it operates. But is it the best sorting technique of all? Let's take a look about another sorting technique from the divide and conquer algorithm, and that is merge sort. What is merge sort? Merge sort is one of the sorting techniques in the divide and conquer algorithm, same as the quicksort. It works by recursively splitting an array into two equal halves, sorting the item, then re-emerge them back. Divide the n element sequence to be sorted into two sequences of n divided by two elements of each. Concurrent sort of the subsequences recursively using the merge sort, and merge the two sort subsequences at the end. Who invented the merge sort? So the one that invented the merge sort is John von Neumann. He developed the merge sort for ADVAC in 1945. A detailed description of analysis of bottom-up merge sort appeared in a report by Goldstein and John von Neumann as early as 1948. So how merge sort works? So for example, we have the following array that we want to sort it. We continuously split the array in half, divide the step until we get the individual step. So let's see. So first we split up the array in half. So we get at 2853 and 9417. Then we split it up again. It goes like this: 2853, 94 and 17, and do it again another one until you get the individual items. So this is the divide steps. Next we use the combine and merge them back. So first we take 2 and 8 and it become like this. So 2 and 8 is still in the order list. Next we take the 5 and 3. So 5 and 3 will be combined and in the sorted order. So 5 is bigger than 3, so it will become like this. And next is 9 and 4. 9 is bigger than 4, so we put the 4 in front and the 9 at back. Same goes as 1 and 7. Next we combine it and into the sorted order with 2, 8 and 3 and 4, 5, 3 and 5. We go like this: 2, 3. 2 is less than 3, so 2 will go first, and then with 8 and 3. 3 is less than 8, so 3 will go first. And next is 8 and 5. 5 is less than 8, so 5 will go first. And then the next one is 8. Next up, so 4 and 1. 1 is less than 4, so 1 will go first. Next is 4 and 7. 4 is less than 7, so 4 will go first. Next is 9 and 7. 7 is less than 9, so 7 will go first, and then 9. Next we use the same steps again until it be in the sorted order. So 2 and 1. 1 is less than 2, so 1 will go first, and next is 2 and 4. 2 is less than 4, so 2 will go first. Next go to the next array, and it will go, and the end of the result, it will become like this in the sorted order. So 1, 2, 3, 4, 5, 7, 8, 9. Now let's compare the quick sorts and the merge sorts. For space-time complexity, for the best and the average complexity of both sort is O n log n, but for the worst complexity of quick sort is O n square, whereas in the merge sort, worst case still has the same complexity as O n log n. For efficiency, merge sort is more efficient and works faster than quick sort in case of a larger array size or data set, whereas quick sort is more efficient and works faster than merge sort in case of smaller array. For stability, merge sort is stable than a quick sort as two elements with equal value appear in the same order in sorted output as they were in the input unsorted array. Lastly, merge sort can work well on any type of dataset irrespective of its size, either large or small, whereas the quick sort cannot work well with large dataset. So in conclusion, merge sort is better than quicksort because of its stability and the worst case complexity, and is more usable for a larger data set. That's all for me. Thank you very much.